Let's see if everything is working fine. So about me, I'm Gianni Ceresa from Switzerland. I'm an ACE director. I blog from time to time. You find everything on that slide. No need for me to telling you all those things. Just about the ACE program, for the first time using this new slide, it's totally fresh. You probably already know about the program. It's this program recognizing and rewarding community members for their technical and not technical contribution to the community. 3 tiers. Go to this link, you find it here on the bottom left. Go to the link on the right if you want to nominate somebody or nominate yourself, mainly for the ACE associate or ACE level. You find all the information online. Now, straight into the topic, because I already know that I will struggle with time. That's what happened so far, at least with this presentation. So straight to the topic, graph databases. Let's introduce that part first. What is a graph? What is a graph exactly? Or better, what a graph isn't. That's really a point that I always make when I talk about graph, because these are not graphs. Those things are charts. Bar charts, line charts, area chart, pie chart. A chart is not a graph, even if in many languages, what we call chart is actually called graph. So people often, let's say, mix the two words. So they think, oh, a graph, it's a chart. Nope. A graph is extremely simple. It's composed by only two kind of objects. You cannot really make it simpler than that. You have the round one, which is called vertex or node. Both names works. And then you have lines, arrows. And this one is called an edge. You take a bunch of them, you shake a little bit, and what you get at the end is a property graph. As simple as that. This is what a property graph is. To make it more obvious and more visual, this is a visualization of a super simple small property graph. So you recognize the rounds, the vertices, the nodes. You see that a vertex has an ID. Every single vertex has an ID just because we need a way to identify them in a unique way. So a unique ID. A vertex, a node, can have a label. In this example, we don't have labels, but a label is an attribute that qualifies the node. It generally tells you what this node is like. Like if you have customers and products, the label is really customer, is product, is a country. It's really something that qualify your node and easily let you know, okay, this node is about a person, this one is about something you can buy, and so on. And then we have the properties, because it's called property graphs. So properties are, again, extremely simple. It's key values. It's always key values, one key equal one value. And the interesting thing is the list, so the number of properties is totally free. One node can have no properties at all. Another node can have one or two properties. The next one can have a few hundred or few thousand properties. It's totally free and dynamic. So in the same graph, the number of properties is not correlated node to node. They are all separate, all independent in a way. So you can have a mix of totally mismatching number of properties and list of properties just because that's what make a graph. So that was the nodes. What about the edges? Well, the edges are again extremely simple. They connect two nodes. There is always one node align another node. The edge will never connect one single node or three nodes or more. It's always two single nodes. And the edge again has a unique ID. Again, it's only a technical argument. We need to identify it in a unique way. You will never really use the edge ID. It has no real meaning, no real value, I will say. The edge again has a label. The label in this case, it's always there because it's what qualifies the edge. And the label is often an action. In this case, it really tell you, okay, for example, it say Josh created Ripple or Marco knows Vada. So it really give you what is the connection between the two nodes. Properties. Edges can have properties. It's the same thing as the nodes. So edges properties are key values always, and then a totally free number of properties. One edge has no properties, another one at 200 properties. It's totally free. And the edges can have just one line. It's a bidirectional edge, or like in this example, you see that the edges always have an arrow at the end. So it's really a directed edge. If we look at Marco and Vadas on the left part of the graph, the arrows say Marco knows Vadas. Vadas has no idea who Marco is. So it's really a directed edge. It only goes in one single direction. This is a property graph, extremely simple. Some examples, or actually before the example, let me make you I will not say a comparison, but let me position a graph compared to a relational database. Most of you probably knows relational database. So you have a bunch of tables, you have joins between those tables. If we take an example, one given row in a table always has the same column as every other row in the same table. And the join is not defined at the row level, it's the table that is joined to another one. And then you can also have, like in this simple example, we have like a mapping table which join two other tables with some properties. When we try to transpose this relational database into a graph, it turned out like this, for example. We can say one table become nodes. So one row of one table become one node. One row of one other table become another node. But then the mapping table, instead of making it a node again, well, we can make it an edge. Just because on our edge, we can set properties. So the attributes that were stored in the mapping table, in this case, become properties of the edge. And because every single node has a different number of properties and the edges as well, it's like if in your database table, every row would have different columns. This is really the difference. It's like going a level deeper in granularity. The joins are the row level. The number of columns is defined at the row level. That's really how the two compares, I will say. Some quick examples. This is not me painting in my free time. I will not be able to do those things. This is a simple graph of data lineage, for example. When you make a data lineage of your database, your ETL, and your analytical platform, and then you ask yourself, oh, what happens if I remove this, if I drop this column from a table? Well, in the graph, in just seconds, I get a simple list of objects that I need to edit and just make sure that the change in database will not break anything. In this case, I go from 45,000 nodes and 105 edges to just 85 nodes. 45,000 objects, there is no chance I could do it by hand. I will never be able to check by hand the impact analysis. While a list of 85, well, yes, I can process one by one and fix them. So the graph really find all the connection in seconds and even less than that. Another example for detections. When you want to do some money laundering or VAT frauds, you just create loops and you send money around it. At some point, the money come back to you. Well, the graph again can easily detect those loops. Doesn't matter how many steps there are. It can be like a 2 steps loop. It go and come back. It can be a 10 steps loops. It come back. The graph will always detect the loops, while in the database, if you have a relational database, because of the dynamic size of the loops, it will be more tricky to find them. The last example, something we are almost not used to do anymore when you want to travel, either by plane or by train or by public transport, going from one point to another one. If you graph the public transportation system, you can find the shortest path in time, from a time point of view, or you can find the cheapest one. So thanks to the graph, you can find which path will connect you from A to B. So how the graphs looks like in Oracle? Well, Oracle developed something called PGX. PGX is really the graph engine. And because Oracle already has a bunch of tools like database and so on, they say, okay, we're not going to reinvent the wheel. So we keep PGX simple. It's really just a graph engine. It's just a piece of, it's a brain. It's a piece of brain powering the graphs. But for storage, they recycle other things. For example, the storage for PGX can be the relational database, can be a NoSQL database, can be the file system with flat files. So there are various kind of storage that you can use, but it's not something that PGX redeveloped. They didn't create a real interface on PGX. They just say PGX as a REST web service. So you speak REST with PGX. You can call whatever you want via REST request, and PGX will answer you by the REST answer. So you can really interact with PGX from anything. It can be Java, Python, JavaScript, a web page, whatever. It's really extremely easy to interact with PGX. This is what makes graph smart from an Oracle point of view, PGX. So this is the graph introduction. Now, the other part of the talk is about machine learning. You already got machine learning in a bunch of talks today, so you probably already know all those things, but let's make it super quick. Machine learning is one of the buzzwords of the last years. It's everywhere. I'm just waiting for Microsoft to add machine learning in Notepad, and then I will get it everywhere, because every single product started adding machine learning as a new feature in the last months and the last 2 years. And there are various ways, various levels of machine learning. There are super simple one, there are super complex one. There is this slide that I took from Habi, and I like it because it kind of positions things a bit. So on one side, you have statistics, all the mathematical things. On the other side, you have computer science, all the programming languages, databases, and so on. And machine learning fitted there like when the two cross. So it's a way to apply statistics by using computer science tools in a way. To make it extremely simple, don't take this as a definition of machine learning. It's just a way to extremely simplify things. A lot of linear algebra, vectors, matrices are everywhere. Bunch of algorithms. Shake a well, what you get is machine learning. Google for it, you will find definition about it. I'm not going to read them. They are on the slide if you want to download them. Google for machine learning definition, there are tons of it. So one important aspect that's most of the time machine learning really depend on what do you feed it with. The better you prepare your model, the better it will perform. Let's do an example. Francesco, a NES director from Italy, he saw a little house one day and he just drew it. It's really him, it's not his daughter, it's really him drawing this thing. And he say, oh, let's ask the machine, how much can this little house cost? So he tell me, yeah, machine, please tell me, I have a little house, it's yellow, how much? And the machine say, no idea. Okay, it's not only yellow, it's also 120 square meters. It has been built 45 years ago. It's located in Bern, in Switzerland. How much? No idea. Okay, Francesco keep telling me a bunch of attributes. He keep describing this house in details. He gives me 1,000 features describing this little house. How much? No idea. Machine learning is not machine guessing. The machine will not guess a price for your house. But if we take our machine, we feed it with like a 100,000 data set of attributes of houses with a real price next to it, and then we ask, okay, but now my little yellow house, how much? The machine can say, yeah, based on what I learned from your training data set, now I will say that your house could cost 1,200,000 and something Swiss francs, way overpriced for that yellow house. So is training always mandatory? Most of us always believe that machine learning always starts by training. It's generally true. It's not wrong, at least most of the time. Sometimes it's not really the case, or better, the training is kind of implicit. And we will see this part a bit later in the slides. So we are finally back to the real topic. Now, introduction of graph done, introduction of machine learning done. What about machine learning and graph databases? Still have half an hour to give you everything I have about it, kind of. To make it super simple, there are kind of three groups of machine learning approach with graphs. First one is using graph algorithms to generate new insight, to generate new information. So we use an algorithm to generate something that doesn't exist by default in the graph. A second approach would be, let's take the graph, export new features, and then I go back to my classical machine learning pipeline. So I go back to my Python machine learning approach, or to my Sage machine learning approach, to my R thing or my database. So I just export information, and then I will use the classical machine learning tools. The last one is, let's really bring machine learning into the graph and see what happens. I'm now going to cover the three of them to just show you what they can do and how. First one is about algorithms. For example, you have a small shop. You have customers on one side, you have products on the other side, and the edges connecting the two are orders. When a customer buys a product, there is one edge that is created. And now you are trying to find out similarities between customers For example, me, if I am a new customer, you try to find in the system somebody looking like me to suggest products that I could be interested in. If a customer is similar to me, I will probably buy the same things. How can you do that with a graph? For example, using personalized PageRank. Most of you know PageRank. Google started with PageRank, was about finding the most important page thanks to the connection it had around the World Wide Web. So personalized PageRank is the same thing, except that you personalize the result. So you say, start from this node or this set of nodes, and those one are the most important one. So the PageRank will not just be generic over your whole graph, but it will say, these are key elements and these are more important than everything else. And then I start doing the PageRank all around. In this super simple example with 3 customers and 5 products, all of you can easily see just by looking that which one of customer 2 and 3 is more similar to customer 1. It's obviously 3 because it has 2 common products instead of 1. And if I look at the result of my PageRank based on customer 1, that's what the system tells me. The score is not a percentage, it's not money, it's really just a score. So who is the more similar to customer 1? Well, it's customer 1 itself. Makes sense. Who's next? Customer 3 and then customer 2. Nothing complicated, but now think, if you have 10,000 customers, you have thousands of products, hundreds of thousands of orders. You will not see it by yourself just by looking at the graph. But the graph can run personalized PageRank in just seconds or even less and give you the answer in like that. No time at all, you get your answer. You get your, this customer is similar to you. So maybe these are the products you have to suggest. This is a way to do machine learning just because I'm not giving anything more to the graph. I just say, graph, please, can you calculate the page rank based on this node as a personalized one? And the graph will start looking around. We'll analyze the whole graph, so the training part is just done on the fly because it will start going around the whole graph to calculate the page rank. It's not me doing it. I'm not doing anything more than just say, please give me the answer. So it's a kind of machine learning. The graph engine does everything by itself. Talking about algorithms, out of the box in PGX, the current version being the 20.1.1, you find it called as graph server 20.3.0.0.0. The PGX numbering is a bit out of sync with the graph server number just because of internal reasons. So by default, in the current release of PGX, you find 43 algorithms. I just counted them this morning because they keep changing. And on the screenshot, you can see the list. The documentation categorized them so you can easily find out, for example, ranking and walking algorithms. You can find pathfinding algorithms or connected components or community detection. So you really have algorithms for a bunch of things, a lot of things. If you don't find what you need, no problem, write it. You can write it in GreenMarl. It's a language to write graph algorithms. You then compile it and use it in PGX. Or easier one, you can use Java. PGX at the really beginning was using GreenMarl algorithms. Now they have all been written in Java. And if you go in the documentation, for most of the out-of-the-box algorithms, you can find actually the Java code. So you can easily customize that code, compile it, and you have your own custom algorithm. As simple as that. Second approach, how about exporting features from a graph and just doing machine learning somewhere else? So machine learning by default is generally seen as a matrix. You have one row for every single sample, and the columns are the features. So if we export some features from our graph with all the sample, we can then run machine learning on top of it. How can we do this thing? It's extremely simple, again, just because I can run a query on a graph. My query result is generally like a tabular kind of result. There are rows and columns. So I can export this thing. I can load it somewhere else and do something on it. So let's imagine I run some algorithms. I can run PageRank. I can run some other algorithms on my graph. I can just get properties like number of edges for every single node, whatever I want. So I'm generating new information. Then I do a query on my graph. I select all the features I need. Most important, I will select the score of the page rank. I will select the number of edges. I will select every other information I generated on my graph by calling algorithms before. And once I did the query, I just export it. Can be a CSV, for example, can be a let's load this thing in the database table. And once it's there, I just do my machine learning cooking with my common tools. I can just extend a database table, for example, with features coming from the graph, and then using the database to run machine learning. I'm just adding new features. The idea is really, let's use the graph to make machine learning more powerful, to give it an extra kick. If your machine learning was quite good with the set of features you got, by adding a little touch of the structure of your data, how they are connected and so on, you can get a more precise model, predicting better things or giving you better results. In general, the more features you have, the better they are, and the better the result. So if I get more features out of my graph to extend the default set of features from my machine learning job, I have chances that my model will perform better. As simple as that. And now the fun part. This is the third approach, is let's really bring the machine learning from outside into my graph. This is really the fun one and the most complicated one. So how can we turn a graph into a matrix? Because we saw that machine learning speak linear algebra, so it matrices and vectors and so on. A graph doesn't look at all like a matrix. A graph is not a set of vectors, it's nodes and edges. How can we translate one to the other? So in PGX 20.1.1, there are 3 built-in algorithms doing this kind of job and doing machine learning into the graph. One is called DeepWalk. It's a vertex embeddings algorithm. One is PG2Vec. It's a graph embeddings. And the last one that has been added only a few months ago is the supervised GraphWise. It's vertex embeddings and classification. Just a little note, they are there in PGX 20.1.1, but the public version that you can download right now will not have this part. I have it thanks to, for reasons. They will come soon to the public release. They are planned. They will be soon part of the public one. They were publicly in beta before. Now they are just not in the current release, but don't worry, they will be soon back. So let's have a look at DeepWalk. Let me take you through DeepWalk and really explain you how DeepWalk works and why it's so powerful and so great. DeepWalk is super simple. So you have a bunch of inputs. You have the graph first, then you have some parameter, the window size, embedding size, the walk supervertex, walk length, and you start doing some for loops. You walk through your graph, you do a shuffle first, then you do a loop over the number of walks. You do a random walk, you apply skipgram, and done. What is skipgram? It's this one. It's super simple. For each, for each, for each, and for. You do some cooking, done. That's deep work. I told you it was fun. It's super simple. It's super nice. It's really fun. Okay, I will show you visually what it does. It does a random walk on the left. It generates a bunch of, I will say, matrices and vector on the middle part, and then it generates a vector representation of a single node at the end. Deep work, as simple as that. When I saw that, it was Chinese, so I started taking some more time to understand what does deep work really do, because so far it's Chinese, 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 no idea, no idea, no idea. I don't get it. Okay, so the idea is, from a node, you take one node from your graph. You start doing random walks. So you start moving around randomly in the graph. You build a sentence which is just, you keep track of every single node that you visit during this walk. So every single node will have a bunch of sentences if you do many walks. And then with these sentences, you apply what is an algorithm called word2vec. So it's a way using natural language processing to transform sentences into vectors. I will give you more details later on. The result is really, DeepWalk will take your graph, and for each node, it gives you a vector representing the node. So the practical example to show you what happened. Back to school, you maybe remember your time when you were in school. We have one director, we have two teachers, teacher A, teacher B. Each teacher has some students, 5 for teacher A, 5 for teacher B. The director sits in the middle, as simple as that. So now let's imagine we want to build an interactions graph. So what kind of interaction these people have? First thing first, let's forget people. We have to talk about nodes. So every person in this example become one node. So every student is a node, every teacher is a node, the director is a node. And about the interaction, we just say who can speak with whom. For example, the director can speak with the two teachers. The teacher can speak with the 5 students, or he can just go back to the director. And the students are sitting one next to each other, so they can only interact left and right. So for example, if I take the student number 2, he can interact with the one on the left, number 1, can interact with the one on the right, number 3, and he can interact with the teacher in front, 6, and so on. So the graph coming out of this simple school approach is this one. The 7 is the director. He speaks with the two teachers, 6 and 8, and the teachers can speak with all the students, and the students can speak only with the people sitting next to them and with the teacher in front. So this is the extremely simple graph we have as an example. Let's do some random walks. So if I take a start from the node number 1, I start walking around randomly. So from 1 I go to 6. Then randomly walk means I pick a random edge. From 6, I go to 7. From 7, I go back to 6. From 6, I go to 3. 3 to 4. 4 to 6. 6 to 2. I did a walk. My walk was 8-step length. And if I keep track of the IDs of the nodes I visited, I started from 1. I went to 6, 7, 6, 3, 4, 6, 2. So I actually have my path. I keep track of where did I walk. There are some parameters which are part of the algorithm. So it's the number of walks per node. So how many times I start walking from every single node of my graph, and also how long is my walk. The one before was eight steps. So I can also change this one and make it longer or shorter. What is the result? It's really a list of sentences. The size is extremely simple. I have as many sentences as the number of walks per node multiplied by the number of nodes. And the length of the sentence is just the walk length, the parameter I got. These are really sentences of words. They identify each node. It doesn't matter if it's a word, if it's a number, or whatever. The ID of a node doesn't matter. I have my sentence. That's all I care about. Now, in this example, if I take my graph, it has 13 nodes. If I do 80 number of walks per node, and my walk length is 40, the result will be I will have 1,040 sentences of 40 words each. So you see that deep walk, first of all, generate a huge amount of information. From a super small graph, I have 1,040 sentences, 40 words each. So it really grew up with a tons of flow of information first. What do we do with these sentences? What do we do with these walks? So those walks, we have to apply the step number 2. It's we have to turn those words into vectors. How can we do it? Well, it's called sentences, so it's really about applying natural language processing techniques. I don't give you the full details because you can Google about it. It's word-to-vec. Word-to-vec is really a NLP technique. You find a lot of content on Google. The idea is we first translate the sentences into vectors, like numbers, and then we feed a neural network. We do some cooking, and the result is vector for every single node. Practically, what happens is there is a key parameter. It's called the window size. Once we set the window size, what the word-to-vec does is this one. It takes every single sentence and it starts moving word to word, one by one. In this case, the quick brown fox jumps over the lazy dog with a window size of 2. If I take the last example at the bottom of the screen, the word I'm focusing on is fox. So the window size is 2 means I have to look 2 words on the left and 2 words on the right. Means that for fox, I generate a couple of words saying fox quick, fox brown, fox jumps, fox over. So I generate a couple of words. It's really just the neighborhood of the words. It just gives me the context. The context of fox is quick, brown, jumps, and over. And applying those approach to text, you generally find the semantic meaning of words just because of where they are located and what are the words next to them. This is a word-to-vec work. Once I have this couple of words, the idea is really to find which context word, so the one on the right, describe the better the target word, the one on the left. For example, for fox, I have to find which one between quick brown jumps and over describe the most. So it's which word is has more chances to be a context word for fox. And this is where the neural network jumps in and does a bunch of things. I really have no time to tell you how it works in details because even Google will give you a lot of results about it. Word2Vec is not an Oracle thing, it's a common thing, it's an algorithm name, so you can easily find information about it. So this is deep work. Let's see in practice how it works. Hopefully it will work. Okay, here it is. I'm just using a Jupyter notebook because I found it easier to make the job. I start by connecting to my PGX server. I create a session on it, and then I create the graph. You see the graph in the picture, it's really just the graph that I was using before, the interaction graph of my little school. I generated this graph. You can see it as n equal 13, it means it has 13 nodes. E equal 20, it's 20 edges, because it's all the edges with all the directions. Fine. And now I will just execute div work. You maybe remember I told you about some parameters, the window size, the work length, the works per vertex. The layer size, it's how big is the vector representing each node. By default in PGX, it's 200. In this case, I just set it by default to 128. Now, let's just run div work with these predefined parameters. I'm now building the div work model. I'm training it. It's really happening on the graph. If I check the graph server, I'm supposed to see it being at full. It was a full load on Java, so it's really running on the graph server. And then I take the vectors that I got back. I just reduce the dimensionality to a two-dimensional vector so I can display them. Here you can see a chart. This one in the middle is the director. And then you can see on red, you have one part of the school, on blue, you have the other part of the school. But wait, there is this guy that is lost. It's supposed to be on the other side of the screen while it's here. And this one, it's also on the wrong side of the screen.
Gianni,
yes?
All we've got is a slide saying demo.
Oh, gosh. Okay, screen share has stopped. So like now not here, not here. Yeah, it always happens at some point. Let's take this one. Do you see something else now?
Yes.
Okay, so let's imagine you were seeing this one till now. Yeah, I know it's easier than to say, okay, but
Cheers.
I say the code is anyway hidden. So I connect to PGX. I build this little graph that you can see in picture. I create it in PGX, and I use my parameters to run it, and then I translate the vectors to a two-dimensional vector, and I display them on a chart. And this is the result. I have my teacher. I have the red dots, which are one side of the school. I have the blue dots, which is the other side of the school, and I have one lost guy and one lost guy. Because what I expect is red one side, green in the middle, blue the other side. That's what I expect to see as a vectorization of my graph. Why it's not working? I mean, I told you the work was fun, was amazing, was so fancy and so intelligent and so smart. Well, it's not working because my graph it's only super small. It's 13 objects, and I'm doing extremely big works, and I'm doing really long number of really large number of works. I'm just overdoing it. I'm doing so many things that I'm just covering the full graph all the time. So as any machine learning approach, you need to tune your parameters. In this case, if I reduce the window size to 6, I just had to write them down before because otherwise I never guess them. The works per vertex is down to 20, and the works per vertex, I make it only 40. Now I'm hoping my school will display a bit better. Oh yeah, I got it. Green in the middle, blue one side, red the other side. So you see that if you take deep work and you tune the parameters, you can really start representing the graph by vectors. So in this case, this is the director, then these are one side of the school, and this is the other side of the school. All the model is doing is really this. I take every single node, I walk around, I build sentences, I take the sentences, I turn them into vectors, and so on. It's doing all those things on the fly in memory every single time that I change the parameters and I update my model. Do you see the slides now, right?
Yeah, we're good.
Cool. So the idea is really deep work. You take every single node and generate a vector. As simple as that. What do you do with those vectors? Well, you can export them and use them as features for your standard machine learning, or you can actually do the real machine learning in the graph, because as you train the graph, the model in the graph, you can also call a function called compute similars to say, hey, based on the vectors, can you tell me which node is similar to this one, for example? An example, a practical example of deep work done by PGX. If you take the DBpedia graph, which is the Wikipedia in English graph, all the pages, all the corner categories, all the connections. So it is 8 million and something vertices, 165 million edges. It takes a bunch of RAM, so you better have enough CPU and RAM for it, but you can do it. You train deep work on this one, and you say, let's take Albert Einstein. It's a page in the DBpedia database, and I say, thanks to deep work, can you please tell me who is similar to Einstein? Not looking direct connection, because there are not direct connection in the graph. The graph is really just pages attached to categories and topics and so on. Say, which other page looks like Albert Einstein? So with a similarity of 1, it's like 100%, it's Einstein himself. Once again, there is nobody else that looks like me as myself. So it's normal that the first result is himself. And I say, yeah, but there is a page about physics which looks like can be quite similar to Einstein. As far as I remember, Einstein did physics things. And then we have Heisenberg, Feynman, Planck, Bohr. I mean, it's all guys that did things with physics as well. They all worked on similar topics. We have also quantum mechanics, special relativity. So you see that on a huge graph, without direct connection between objects, deep work really find out what else in the graph looks like something that I ask for. This is really the power of deep work. Because it's based on random walks and on a neural network and so on, every single time you execute it, the result will be slightly different. You cannot really repeat it. So it's always like run it now and cross your fingers that it works. But it's always different, but in theory, it's, let's say, constant in quality. As long as you don't change the parameter too much and they are right, the quality of the result will always be similar in a way. So now back to the point. At the beginning, I told you, you have enough bunch of properties. Every vertex can have infinite properties, every edge properties. When I took you through deep work, I never mentioned once a property. What are properties? I loaded my graph with properties and now I didn't use them at all. Yep, that's it. Deep work couldn't care less. It only look at the structure of the graph. It only look at nodes, edges. The content of the edge, the content of the nodes, I don't care. Deep work doesn't look into your graph at all. You just look at the structure of it. It's extremely basic. It's structure based. The content doesn't matter. So this one was one of the powerful machine learning algorithms in graphs. A second one is paragraph 2vec. It's really similar to deep work. It's just like one level up. It doesn't look at random walks on nodes and edges. It looks at subgraphs. It tries to find subgraphs looking like each other. So for example, it will say a subgraph will give me a paragraph composed by sentences, and then it do the same job as before. It's exactly the same thing, just at a different level. Paragraph 2vec is a standard algorithm. Oracle did some cooking. They call it the secret sauce recipe. I have no idea what is inside and don't say it. They say, we just consider multiple properties. rather than a single one. Um, because it's like deep work, but a different level. Deep work doesn't care about properties. What do you look for in properties? Oh, it's secret, we cannot tell you. Take it as a fact that there is a secret sauce somewhere that do things. So they use the multiple properties. When they generate traces, they consider edges as words. No idea what it means again because it's black box. They do things. The key point is you run paragraph to vec, you train the model, you apply it. Don't ask yourself what is doing inside. It's an machine learning algorithm. It does things. You don't have the details for this one. The third one is the last one that joined the team, the supervised graph-wise. You find the details written on the documentation that is linked at the bottom of the slide. I must admit that I still never run this one just because I got the PGX version containing it only a few days ago. I had no time to really play with it and execute it. It looks great on the documentation. It looks quite powerful. I cannot wait to use it. Let's see where it takes me. The conclusion of this whole story, taking you through the graph and the algorithms and machine learning. So first point first, PGX, which is this property graph brain, is actively developed by Oracle. They keep improving it. They keep changing things every quarter, kind of. It has a lot of documentation. You can go on Google, you search for Oracle property graph or PGX. You find documentation, you find tutorials, you find a lot of things taking you through how to get started with it. Out of the box for free, because yes, property graph are free since last December. So out of the box for free, you get about 60 algorithms. I told you it was 40 something at the beginning. There are some variants. So for the same algorithm, you have 2 or 3 variants. That's why the total is about 60. Half of them, I have no idea what they do. I don't understand the name. I don't understand the description at all. It's really graph theories. So sometimes it's fairly tricky. But if you really read it through everything, you will get a hint about what they do and why they do it. And at least most of the time, I just run them and I try to figure out, are they helping me? Yes or no? But yeah, half of them are perfectly well understandable. Half of them are a bit more tricky. Machine learning algorithms, they are there. They exist. They are in beta since PGX 19. They have been available publicly for some time. It was the Oracle Labs PGX release. Right now, you cannot download that version anymore. So right now, you cannot get it. Not this little part, not the deep work part. You have to wait, I guess, maybe next release or the first one next year. It's supposed to come. So it's a few months to wait before to get deep work, PG2VEC, and the GraphWise thing available, but it's coming, at least coming soon. That's what I heard. I'm not Oracle, so don't take my word as I need a safe harbor statement here, but details. The key point is how can you do machine learning in graphs and what is the best approach for it? I will say the best results for machine learning and graph is really mixing things. That's what machine learning is like. You never stick to one single technique. You mix multiple techniques. So you generally, I will say, you will use a graph to generate information. You generate new features that you will export and just use them to make your machine learning pipeline better. You can use deep work to generate the vectors, export them. So for every single node of your graph, you will have a vector of 100, 200 elements. So it's 200 features. It's a lot of features that you can really use to make your machine learning models better, smarter, predicting better things. The idea is really you take your source data and you enrich it with a touch of the structure. Most of the time, machine learning only look at the attributes of things, only look at the content of a table. You just say take, okay, I have one house, it's this color, this size, and so on. It doesn't look at the structure, how things are connected to each other. This is where the graph will bring you this structural point of view. You just extend your machine learning by adding how does the structure of data looks like. And with it, your machine learning will definitely work better. And this is it for my presentation. I even managed to stick into 45 minutes, which is quite uncommon, I must admit.
Oh, great stuff, Gianni. So if you've got any questions, you could put them in the chat, or there's the question and answer box. So I'll give you a couple of minutes to start typing questions in, because it can take a little while for people to type in their questions. But yeah, I've never used PGX, so looks quite interesting. So it's quite a new thing then.
I must admit that it's still a bit unknown, because it has been part of the database itself for some time. So when you install the database, it was just part of the database home. In the Oracle home, you found it there in the middle. And that's why nobody knew it, because the DBA said, don't touch my database home. So nobody could ever touch it. Now it's available as a standalone separate product. So you can install it saying, I just connect to the database to load a graph. I don't mess with the database. So DBA, don't blame me. I just load data and write things back. So now it's start getting a bit more traction, I must say.
You should always blame the DBAs, Gianni.
I do that daily. So yeah, nothing new there.
Okay, well, all we've got is thank you for the nice presentation about PGX. And no questions so far.
All I can say is stay tuned. There are new things coming to the cloud for graphs as well, finally. So you will soon be able to do easily graph in the cloud, I guess. If you want to get started now, you can use the free tier. You create an autonomous database with the free tier, so it's free. You create your graph in this autonomous database, and then on your laptop or even on a compute instance on your free tier instance, you just spin up PGX, load the graph, and start querying it, start using it. So you can really get started for free, fully free.
Cool.
Yeah.
Well, I don't think we're going to get any questions. So as a DBA, I'll say thank you very much, Gianni.
I mean, one key point, graph will not fight a relational database. They only complement it. That's always my point. It's just, they complement each other.
Of course.
So it's not me against DBAs. It's next to each other.
Oh, always working to get the best result we can for the business.
Yes, that's really the point.
Okay, thank you very much for your time, Gianni. It's very much appreciated. And see you all at the next talk.
Thank you very much. Thank you, everybody. Thank you, Neil. And let's enjoy the next one.